Hello, everyone. So today we are going to discuss about the small scales in turbulence. One of the most important topics in turbulence theory is going to be covered today. In the last class, what we did was we looked at the varying range of length scales. We started by considering the Navier-Stokes equations. We looked at the scales in which each term becomes active, the inertia and the viscous, and we realized that at high Reynolds numbers, by definition of Reynolds number, the viscous effects would become negligible, isn't it? So then can we actually make that assumption of neglecting viscosity, neglecting viscous effects? Because they do have a role to play, especially in flows involving solid surfaces. The no-slip condition would not be satisfied. Boundary layer would not exist if you didn't have viscosity. So that made us think, as pointed out by Tenikis and Lumley's book, that made us think maybe we have to think of Reynolds number as inertia at a different length scale and viscosity at a different length scale. And that makes sense, right? Viscous effects are more dominant at the small length scales. It is true at the large length scales the viscous effects won't be as dominant, and they can indeed be neglected because they are negligible. But on the other hand, you cannot do away with viscosity, and that's actually what we are going to continue here, especially since we are going to talk about the small scales of turbulence. You cannot do away with viscosity because viscosity has a role to play. Dissipation at the small scales happens because of viscosity. That's the main topic for today's class. So far we've been talking a lot about large length scales, isn't it? Because they are indeed the most important. They are what supplies the energy to the turbulent flow. That is where the energy is pumped in. So they are responsible for transport. They are responsible for transport of momentum, transport of impurities, contaminants, right? Any kind of species. They are responsible for that. They are mostly responsible for that. However, there is another effect that is also in play, and that is the viscous effects. Now, if you think about the large eddies, large scales, they are as big as the width of the flow. So if you talk about a pipe flow, they are as big as the diameter of the pipe, order of magnitude. If you talk about flow over a cylinder, they are as big as the diameter of the cylinder. Flow between two plates, as big as the distance between the two plates. Boundary layer, they are as big as the length of the plate under consideration. So here, that large length scale in the boundary layer case would be of the same order as the boundary layer thickness. However, at very small length scales, viscosity starts to play a role, right? And the smallest length scale is the length scale at which viscosity is active, the length scale at which dissipation is active. And here, viscosity plays a huge role. So keep in mind, the smallest length scale doesn't mean micro scale where continuum is not valid. So continuum is still valid. We are only going down to that scale. Huh? We are not going down to the point where molecular scale becomes important. It is not. Molecular diffusion is important. That happens because of viscosity. So you have these small scale fluctuations that are generated due to the nonlinear terms. We know that. That is representative of the convective transport which generates the small scales. The scales break down. Large scales break down into smaller and smaller scales because of their nonlinearity. But what happens is viscosity, the viscous effects, they prevent the generation of infinitely smaller scales. So one can argue, so when we started this discussion, we know that we have large scales that are generated which are as big as the width of the flow. They break down into smaller and smaller scales. So there is this scale breakdown that happens. But what is the lower scale that is generated? So that is determined by viscosity. So viscosity, what it does is it prevents the generation of the smallest scale that is ever possible. Because even before that, dissipation becomes dominant, and the small scales dissipate all that energy into heat. So it prevents the generation of infinitely small scales of motion. So this doesn't just go on forever, right? The scale breakdown from large scales to small scales, it doesn't go on forever. It eventually stops where the dissipation becomes dominant, and then all the energy is just dissipated to heat. That is what happens. So this happens, obviously, like I was saying earlier, because of viscosity. This happens because of kinematic viscosity. What happens here is, at large Reynolds numbers, it is expected that the magnitude of nu, kinematic viscosity, is so small that the viscous effects tend to be really small, negligible. But there's another effect that happens here. The nonlinear terms in the Navier-Stokes equations counteract this threat by generating motions that are small enough to be affected by viscosity. So we would think, okay, at the large scales, at high Reynolds numbers, viscous effects can be negligible, right? So can they be neglected? No. So immediately what happens is the nonlinear terms generate small scales that are small enough for viscosity to play a role. So in a way, you cannot just do away with viscosity, because viscosity has a role to play in dissipation. And dissipation is one of the main attributes of turbulence, as discussed earlier. That role is played by viscosity alone. So you would think, okay, at high Reynolds numbers, inertia over viscous effects can be neglected because they are negligible. Not so fast. What happens here is the nonlinear term is active always. It keeps generating small scales which are dissipated, which at the right scales, at the appropriate small scales, are dissipated by viscosity. So this smaller scale of motion automatically adjusts itself to the value of viscosity, meaning the scales break down, keep breaking down until viscosity becomes dominant. So that's what we mean by there seems to be no way of doing away with viscosity. As soon as the scale of the flow field becomes so large that viscosity effects could be neglected, right? The flow creates small scale motion, thus keeping viscosity effects at a finite level. And this is in terms of dissipation. It is in terms of dissipation rates. So that is where viscosity comes into play. So if you have a flow that has only a lot of large scales, then viscosity might not play a role there. It might not play a dominant role there. It might not play a finite role there. So then what happens is the large scales are immediately broken down into small scales. Then viscosity has a role to play. And this keeps happening. That's the role of viscosity. Now, we know that large length scales are associated with large time scales. They take longer time to move from one point to another because these are large scale motions. On the other hand, small scales, small length scales are associated with small time scales. Because they are small in size, they take shorter time to move from one point to the other. So if small scale motions tend to have small time scales, and this is really important. This is the basis of one of the most important universal theories of turbulence. If the small length scales have small time scales, meaning what? What does small time scale mean? Meaning they tend to move very fast, that's one thing, and also they tend to exist for a very short period of time. That time scale determines the amount of time that they actually exist. They have a small time scale. The large length scales have a large time scale, so they are around for a while. Whereas the small length scales have very small time scales, so they're not around for a long period of time. In fact, I would argue that they are there for a very, very short period of time. After that, they are immediately dissipated. Dissipated to what? Dissipated to heat. By whom? By viscosity. The large length scales, on the other hand, they are around, they keep generating energy, and they break down into smaller and smaller scales. Eventually, once the small scales are formed, then they immediately disappear. When I say disappear, meaning the energy just dissipates to heat. So for all discussion purposes in this class, I'm just considering large versus small. Obviously, there's a wide range of length scales, but I'm dividing the scales into large versus small. I don't have any intermediate scales. I have a set of scales that I call large. I have a set of scales that I call small. The small scales are affected by viscosity. The large scales have inertial effects, which get broken down into small scales. So I have only two bins, large and small. This is mainly for discussion purposes. Of course, in a turbulent flow, you have a wide range of length scales, and a lot of things happen in the intermediate scales. Yes, but for the purposes of describing this theory, I am just considering two bins. Energy goes from one bin to the other, the large to the small. That's it. And from the small, it gets dissipated into heat. So, coming back to the time scales, if the small scales have smaller time scales, meaning what? They are not around for a while. They are around for a very short period of time. They immediately dissipate to heat. So the large scales get broken down into small scales, and the small scales dissipate to heat. And these have a very small time scale. So if these have a small time scale, it is fair to assume that the rate of energy supply should be equal to the rate of dissipation, isn't it? Because as soon as the energy goes from the large scales to the small scales, they dissipate because the time scale is very small. They have really short time scales. So they are not around for a long period. They are around for a very short period of time. They immediately dissipate to heat. So in that sense, the rate at which energy is supplied, the energy is supplied from the large scales to the small scales, should be equal to the rate at which energy is dissipated, because they don't stay for a while. And that's what I mean by, because the net rate of change of small scale energy is related to the time scale of the flow as a whole. So this net rate of change should be small compared to the rate at which energy is dissipated. This is the basis for Kolmogorov's universal equilibrium theory for small scale structure. What you have is the small length scales have very small time scales. So they only stick around for a very short period of time. They immediately dissipate to heat through viscosity. If that is the case, then one can assume that the rate of energy transfer from the large scales to the small scales is the same as the rate of dissipation, because everything happens instantaneously almost. That's our argument, and that is the basis for Kolmogorov's theory. So this essentially suggests that you can have parameters governing the small scale motion determined by mainly two parameters, right? We talked about velocity fluctuations. We talked about the rate at which energy is pumped in, the large length scales, nothing of that sort. The rate at which energy is transferred to the small scales is entirely determined by the rate at which energy is dissipated. And what does the rate at which energy dissipated depend on? It depends on the dissipation rate. So let's call that epsilon, and this is always per unit mass. So it is dissipation rate per unit mass. Remember, this is dissipation rate at which energy is dissipated. So it has units of energy per second, per unit mass. So that is why it is going to be meter squared per second cube. And of course, the dissipation happens because of viscosity, so it will depend on the viscosity. Kinematic viscosity, so units are meter squared per second. Using these two parameters alone, you can come up with a set of length, time, and velocity scales at the small length scales. So you have eta, which is a small length scale, the smallest length scale possible, in fact, in turbulent flow, identified in turbulent flow, a time scale, the smallest time scale, and the smallest velocity scale. These equations are determined purely based on dimensions. So if you think about it, just as a simple exercise, nu has units of meter squared per second and epsilon has units of meter squared per second cube. So if I take nu cube over epsilon to the 1/4, what I get is meter to the 6 divided by second cube, isn't it? Divided by meter squared per second cube. This whole thing to the 1/4. And then the second cube and second cube get cancelled. And what I have is meter to the 4th to the 1/4, which is meter, which is what this is. This has units of meter. It is a length scale. It is a small length scale. These scales are referred to as the Kolmogorov microscales, which in his paper in the 1940s, he called it the inner scales at that time. The paper was originally written in Russian, translated later. So the Russian translation came out to be called as inner scale. So that is what he called it in his paper, at least based on the translation at the time. So we now call it the Kolmogorov length scale, the Kolmogorov time scale, and the Kolmogorov velocity scale. The Kolmogorov length scale is probably one of the most important developments in turbulence. Mainly because even to this date, this is used as a criteria for determining whether your experiment or model is well resolved, can be accurate enough or not. Purely based on this definition. The Kolmogorov length scale is defined as nu cube over epsilon. If you have a way to calculate the dissipation rate, which is not easy to do in a turbulent flow, then you can estimate the Kolmogorov length scale like this. Obviously, there are different ways to do this, and we'll discuss those as well in the next few classes. But if you have a way to calculate the dissipation rate, this is one way to calculate the Kolmogorov length scale. Now, viscosity is of course known because it is a property of the fluid. So, like I said, this is the Kolmogorov length scale. This is the Kolmogorov time scale. And you will see that these equations were purely arrived at based on dimensions. That's it. We consider these length, time, and velocity scales only to be dependent on epsilon and nu. That's it. Dissipation rate and viscosity. So you can actually do a Buckingham Pi analysis and come up with these equations, with your independent variables being two, which are epsilon and nu, and your dependent variables being eta, tau, and v. That's it. It's as simple as that. And you could come up with these relationships. Independent variables being viscosity and dissipation rate. Again, I cannot reiterate enough the basis of this theory. The idea is small scales, small length scales have small time scales. So the small length scales do not stick around for long. They immediately dissipate into heat, which means the rate at which it is dissipated should be the same as the rate at which energy is transferred. If the rate at which energy is transferred is equal to the rate at which it is dissipated, then there are only two parameters that determine the rate of energy transfer, which is dissipation rate and kinematic viscosity. And that is what we came up with. These are called the Kolmogorov microscales of length, time, and velocity. So that's one point. Secondly, if you have a Kolmogorov length scale and you have a viscosity, you can come up with a Reynolds number based on the Kolmogorov length scale. And this is what is another interesting thing here. We assume that the Reynolds number based on the Kolmogorov length scale is 1. Why such a number, 1? Well, the idea is if the Kolmogorov length scale is the smallest length scale that is possible in a turbulent flow, then the Reynolds number can be sort of the smallest whole number that is possible. Okay, so and that is of the order of 1. So 1 is a small number. So using that, you can come up with a relationship with that. So eta V over nu, which is the definition of Reynolds number, is equal to 1. So what we are trying to say is that the small scale motion is quite viscous, isn't it? And the viscous dissipation adjusts itself to the energy supply by adjusting length scales. What do I mean by small scale motion is quite viscous? You have a Reynolds number that is very small, 1. The number 1 is used for convenience. Obviously, it can be 2, it can be 3. So the order of 1. It is used for convenience so that we don't need any other constants. So eta V over nu is equal to 1, meaning the Reynolds number is very small. So that small scale motion is extremely viscous. Inertia terms are very negligible there. So if they are very viscous, viscosity plays a big role in dissipation. And what the viscous dissipation does is the rate at which it dissipates, isn't it? That's what we mean by it adjusts itself to the energy supply by adjusting the length scales. So the scale breakdown keeps happening until viscosity becomes active. And the dissipation rate adjusts until you have the right length scale. So it adjusts itself to the energy supply, because the energy supply is going to be equal to the dissipation rate. The rate at which energy is supplied becomes of the order of magnitude as the dissipation rate because of the very small time scales. That is what we mean by this. So what we have covered here in this class is this small scales of turbulence. And we started by thinking about what are the time scales associated with the small length scales. What are the time scales associated with the large length scales? That got us to think, if the small length scales have very small time scales, then possibly here what happens is they are dissipating immediately. As soon as this small scale bin, the length scales in the small scale bin are formed, they are immediately dissipating because they have very small time scales. So they don't stick around for a long time. So if they are dissipating at such a fast rate, then the energy supply would also be the same as the dissipation rate, isn't it? Because it's energy supplied, transferred, dissipated. Energy supplied, transferred, dissipated, so on and so forth. It immediately happens. So there are only 2 parameters that we need to be focused on: the dissipation rate epsilon and the nu. This is what Kolmogorov used in order to determine what we now call as the Kolmogorov length scale, the Kolmogorov time scale, and the Kolmogorov velocity scale. It's very interesting, right? So if you think about these length scales, it is and this is going to be provided as an exercise for you. We are going to use Buckingham Pye's theorem to come up with these equations. It is the theory, it is the basis of the theory that was seminal here, I should say. The fact that he used the idea that small length scales have very small time scales, and hence the dissipation rate would be equal to the rate at which energy is transferred. That is what was a significant momentum shift. And today, if you are actually doing a turbulence simulation and you want to try and figure out what is the grid that you need to use in order to resolve the smallest length scale, you make sure your grid size, the smallest grid size, or your average grid size is as small as the Kolmogorov length scale. And this is the basis for that. Later we will see how to relate this Kolmogorov length scale to the Reynolds number. And so before running a simulation, a turbulent simulation, you typically don't have the value of dissipation rate, but you have the value of Reynolds number typically. So then you could use that to estimate what the Kolmogorov length scale is and try to make sure your grid size is of the same order as that as the Kolmogorov length scale. So direct numerical simulation is one turbulence simulation approach, I should say, where even the smallest length scale is resolved, right? And one of the requirements for those kind of simulations is that the grid size should be as small as the Kolmogorov length scale. And that is the first, I would say, sanity check that you need to do for your simulations. Only then will you know that your simulation actually is going to be accurate. That is how important this. Even to this day, these are parameters that are used to test simulations and experiments. Thank you.